will be given by Dr. Lior Rubenenko. You can see, and he's currently a postdoc scholar at Stanford Department of Geological Science. And he did his undergrad in Tel Aviv University in Israel, and then he did his master degree in the Weizmann Institute of Science, and then he went to UCLA to study under Professor David Page on the remote sensing technique of the Moon and Mercury. And so currently he is now working as a postdoc at Stanford, and his main interest at this point in time is doing machine learning, analyzing the data from, for one thing, from the Lunar Reconnaissance Orbiter, from the D1 team. I think it was led by Professor David Page, was it? Yeah. And if you go to his, go to Google and find that, you will see another interesting thing about Dr. Rubenenko is that he's the editor-in-chief of a popular science magazine in Israel. In fact, he said it's the largest magazine. So maybe after his lecture, we will chase after him, to get more information on how to popularize, how to popularize and energize young audience. Okay, Leo, please start your talk.
So thank you so much, first of all, for inviting me to speak. My talk today, the majority of my talk today will be focused around topics I investigated in my PhD and I presented in my PhD dissertation, all related to the origins of ice and other volatiles trapped near the poles of the Moon and Mercury. And the first thing I think it's important to understand about both these planetary bodies, the Moon and Mercury, is that their poles are these unique environments that because of the unique orbital parameters of both the Moon and Mercury, cause the appearance of what we call permanent shadows or permanently shadowed craters. And what I show in this video here is how does the pole of Mercury, the North Pole of Mercury, looks like as the sun, basically as Mercury goes around the sun, but as the sun goes around the pole from this frame of reference, it casts light on the walls of those craters. But as you can see, the floors of some of those craters remain in total darkness throughout the year. And this is the result of an illumination model, basically, not of photographs. And the reason for that is because Mercury is found in this orbital state that causes its axis of rotation to be always perpendicular to the ecliptic plane. So you can imagine that if you dig a hole near the pole of Mercury, in this case, then this hole, like those craters, would just cast a very persistent shadow. Now, the Moon is similar, it's as unique as Mercury in that sense. Because for the Moon, because it went through a state which is called the Cassini state in its past, it got stuck, quote unquote, in a state where its axis of rotation is again almost perpendicular to the ecliptic plane. In effect, the obliquity of the Moon to the ecliptic plane is about 1.5 degrees. And this again causes craters near the poles of the Moon to cast those highly persistent shadows. As you can see again, as the sun goes around the pole, obviously it's the other way around, but just for the from this frame of reference, you can see that those craters, like Shackleton here in the pole, is constantly shadow. And this situation, according to models, have been going on for billions of years, potentially 3.5, 4 billion years. So those are very old, persistent shadows. And in the 60s, this canonical paper by Watson, Mary, and Brown hypothesized that since those temperatures, since those shadows, the temperatures of those shadows are as cold as space, because the Moon doesn't have an atmosphere to mix heat from the equator into the pole. So those shadows may reach temperatures as low as 50, 100 kelvins. There's no reason why not, right? The only factor, the only reason for the floors of those shadows, or for the floor of those permanently shadowed craters to be warm, is reflectance and thermal emission from the walls of craters. So when you do kind of a probabilistic estimate of what would happen if you put an ice cube or a piece of ice on the floor of those permanently shadowed craters, you find out that due to the low temperature of those craters, the sublimation rate of this ice, even into vacuum, is very low. Basically, molecules can almost not leave, or can almost not leave the surface, or leave the surface at a very low rate. And how low? When you do, again, this calculation, you realize that the loss rate inside a cold trap that's about 100 Kelvin is about 1 meter per billion years. So if you put 1 meter of ice inside a polar cold trap near the moon, near the pole of the moon, then it'll probably take about 1 billion years to sublimate, which is very slow. Obviously, when you bury ice under the surface, then the regolith covering this ice acts like a lid, right? Molecules tend to stick to the pores of the regolith as they travel outside, causing even a slower sublimation rate. And assuming a steady state, you can work out the math and find out that this decreases the sublimation rate linearly with depth. Now, on the surface, molecules also move in hops, just like under the surface, right? They hop from grain to grain. So on the surface, they also move in those ballistic hops that are obviously related to the temperature, what gives them the energy. And again, if you do this really simple estimate of the gravitational energy versus the thermal energy of a water molecule, you find that the hops near the equator, at least, are of the order of 100 kilometers, so pretty big hops. And those molecules can hop on the surface until they reach a cold enough place, a cold trap, and then they just stay there for a very long time, basically. And the question is, how can we detect the size trapped inside those cold traps? So a few of the methods. One method is to use radar. This is a well-known method to detect pure ice on planets. On Mercury, it works beautifully. Basically, you point a radar and shoot radar signals at the moon, and you record them back, and then you can measure the reflectance, what's called the circular polarization ratio. So the amount of waves fired with some polarization relative to the amount of waves that came back with opposite polarization, basically. Now, when the CPR, the circular polarization ratio, and the reflectance are high, then this is indicative of the presence of highly pure ice. So again, pure is kind of a subjective term, right? But a nice deposit that contains almost no regolith mixed into it, basically. Another way to detect ice on the surface is to just look at the brightness of the surface, right? Because bright ice or ice is brighter than the environment. So bright ice should be more reflective than just regolith. And therefore should appear brighter in, for example, reflectance around the 1 micrometer band. What's interesting about Mercury is that Mercury has both dark and bright deposits. And it is hypothesized that those dark deposits that appear inside those permanently shadowed craters in lower latitudes are the result of other volatiles, like organics. So in this case, some comet, according to this idea, comet impacted the surface of Mercury, and different types of organics traveled into the pole. Now, those simple organics were cooked by energetic particles directed by Mercury's magnetic field. And the carbonaceous materials, at least, formed those long carbon chains that darkened them and also made them more stable for sublimation. So even though the ice is lost inside those craters in lower latitudes because the temperature is slightly higher than near the pole, those carbons don't go away. So we're left with those thick or those pure, not necessarily thick, layers of carbonaceous volatiles. And more evidence for that can be seen in images, actually. So if we take an image, a long exposure image of a permanently shadowed crater, like this one, you can see that the edges of this dark material that I just told you about are very crisp, which is probably indicative of maybe the age or maybe the amount that's being deposited, because it's not, for example, soiled by ejecta from craters impacting the side of the ice deposit. Now we can compare those two maps with the model temperature, because we don't have an actual measured temperature map of the North Pole of Mercury. And we indeed find out that in the coldest places, we get the brightest deposits. And in the a little bit warmer places, we get those darkened deposits like this theory predicted. Now on the moon, as we said, the moon looks exactly like Mercury, right? In many, not exactly like Mercury, but the moon is very similar to Mercury. At least the thermal environment of the moon is very similar to that of Mercury. So in many senses. And if we point the same instruments at the moon, we should expect to get the same results. However, we do not. And this is one of, I guess, the biggest questions I think, to me, at least, in planetary science today. Because when we look at radar, with radar reflectance on the moon, on the south pole of the moon, in this case, we find no increased reflectance inside PSRs, permanently shadowed regions. When we look at reflectance, there's maybe a little bit. Here I'm indicating the contours of permanent shadows. So I'm going to kind of flicker them back and forth. And you can see that, for example, in those three craters, the three amigos, the brightness is slightly higher, increased inside craters than outside craters, but not significantly. Nothing like what we saw here, right? Where some craters just pop out, just have a significantly different albedo. However, the moon for sure has some ice, and an important piece of evidence came a few years ago when the M-cube data on the Chandarian spacecraft, the Indian Chandarian spacecraft, was analyzed, and was found that inside those PSRs, the spectra of those PSRs looks slightly different than the spectra of areas that are not PSRs, and it looks exactly like the spectra you'd expect ice to have, basically. So it's a very good indication that the spectral signature of whatever's inside those permanently shadowed craters is very close to that of ice. Another piece of evidence that there's maybe ice on the moon is, as I said, the brightening of its surface. So when we take the data from the poles of the moon and we just bin them by temperature, so we take each basically one of those regions on the moon and just check what's their brightness as a function of temperature, we get an elevated temperature. Sorry, get an elevated brightness at low temperatures. A very interesting feature, which may say something, may not, happens near the South Pole, where at about 100 Kelvin, which I want to remind you is the same temperature where ice starts becoming very stable, a sublimation rate of about 1 meter per billion years. There's kind of a step function. There's kind of a sudden increase in the brightness. And if we sum up the evidence that we just looked at, we can see that on Mercury, ice is pure and thick, because we know that because of radar. However, on the moon, there's no radar reflectance, which means that if there's any ice in the surface, it must be either thin, so not thick, not reflective, or just mixed in with the regolith. On Mercury, it seems like albedo, the albedo data shows us or indicates that ice is in like those long sheets, really coherent. Those deposits are very coherent. But on the moon, we don't really see the same. We see maybe a little bit of brightening inside those craters. And then we have other evidence, which I've talked about, which I haven't mentioned, like neutron spectroscopy that shows evidence for ice on both planetary bodies. We have images of ice on Mercury, but not on the moon. And on the moon, we have other lines of evidence, like UV reflectance, which I haven't shown, and other from other instruments. And again, one of the questions that I think is one of the most important questions in the study of the inner solar system today is what's really causing this difference in the amount of ice. And to answer this question, I think we have to look at the kind of the equation of accumulation versus destruction of ice inside cold traps. So we already covered accumulation. This happens as molecules, let's say from a comet crashes on the surface, shoots out molecules everywhere. Those molecules hop in ballistic hops until they reach a cold trap, a cold region, and then they just get stuck there. So that's accumulation. However, there are many ways in which ice can be destroyed, right? There's more than one way. One way is it can be just, it can just sublimate. As you know, even though the sun is very low in the sky, its rays can be reflected from the illuminated walls of craters, heating up the ice. Another option is that the warm walls of craters just emit thermal radiation, again, heating the ice. A more important mechanism, probably, that's I think maybe was a little bit overlooked in the past few years or the past maybe decade, is photolysis. Photolysis is actually very important in destroying ice, and we're going to go over those rates in a second or in a few more slides. And then there's gardening. Gardening is the impact of tiny micrometeorites, or small micrometeorites that kind of churn the surface. Now, micrometeorites for sure heat the surface or impact the surface. They give the surface energy and heat it, as I said. But more than that, they give it, or the energy encapsulating those micrometeorites is distributed between heating the surface, but also mixing it. And I think it's not entirely well constrained what's the role of micrometeorite heating versus mixing. So maybe gardening mostly mixes ice into the regolith. Maybe it destroys ice completely. However, it is potentially at least a destructive mechanism. And when you survey just papers, you know, I just named a few papers here in the bottom. So when you survey those papers and the accumulation, the destruction rate, the erosion rate they've calculated, you find that the equation of accumulation minus destruction is almost equals zero. So it seems like no mechanism controls the other. It's not like destruction is 2 orders of magnitude greater than accumulation or vice versa. And this means that maybe those deposits, or this indicates that those deposits are in a sort of maybe a steady state, something like that. And that will become important later. Now, to better constrain both the destruction mechanisms and the accumulation, we should know the temperature of the surface. That's very important. The way to do that is, like I've shown before, is to sum the contribution of all the different factors that can heat the surface. Insolation, and then scattering from walls around the shadow, and thermal emission, and of course subsurface conduction, which is more important actually in those colder regions. Now, you can take those models that just calculate ray tracing or ray casting, use those algorithms like ray tracing and ray casting, like in old computer games, to compute the shadows and the amount of radiation reaching every part of the surface, and use that to compute the temperature of the moon and Mercury using topography gathered by spacecraft. You can use an idealized description of the surface, like those 2 canonical papers that imagine the craters to be bowl-shaped, so hemispherical, basically. And then the geometry becomes very simple, and you can calculate the temperature of the shadow just mathematically, which is really nice. And an approach that I've taken in the past is to use what's called Gaussian random surfaces. So let's say we do not know how the topography looks like, right? Like we did before, like let's say near the poles of the moon or Mercury. So let's say we're looking at a new asteroid, or we're looking at a new planet, or maybe we're interested in looking at a scale much smaller than the scale that we can actually resolve the topography. So we have to kind of guess how the topography looks like based on measurements that we have. And one way to prepare something that looks like topography but is random, or one way to attack this problem is statistically, maybe it's a better way of saying that, is to use what's called those Gaussian random surfaces. And to make them, you start with a 2D distribution of random numbers, of Gaussian numbers, and you shape their power spectral density to be that of a power law, basically. And when you do that, the slope of the power law and the height of the PSD above the x-axis would dictate how the surface would look like. But the end result, as you can see here on the bottom, looks a lot like topography, like rough topography. And this instrument allows us to investigate cold traps on scales much smaller than the scales we can resolve the topography using spacecraft information, spacecraft data. On Mercury, for example, we've used that information to constrain which mechanism governs ice accumulation, whether it is an episodic mechanism, episodic delivery, like, for example, a comet impact, or a volcanic eruption, or a continuous trickling of ice from, let's say, micrometeorites that hit the surface and constantly release water molecules into the exosphere. So the story of this starts by kind of just looking at the map of the reflectance of the North Pole of Mercury that I've shown you before. And you can probably see that there's a ring around the pole that's slightly darker, that's slightly greener than areas in lower latitudes. And this low reflectance region, this green low reflectance region, is probably indicative of the same process that's happening inside those individual craters, right? We saw that those individual craters harbor carbonaceous volatiles, long chains of carbonaceous volatiles that are darker because of the chemical processes they undergo because of Mercury's magnetic field. And we cannot, it's not unreasonable to assume this process also happens on a small scale. And we can use that to our advantage and kind of investigate how much ice there is in those smallest cold traps. And to do that, we take this random surface that we've seen before and compute its temperature, assume it's found at a high latitude on Mercury. And from the temperature, we can guess what's the albedo of regions that should hold surface, that should not hold surface ice, but should hold volatiles on the surface, because again, they're more stable. They're long carbonaceous chains, are much more stable than water ice. So in places where the water ice goes away, those chains would still remain. And we can set the albedo of bright regions, of regions cold enough to hold surface ice. And we have the albedo of the rest of the regolith around it. And by kind of calculating the average albedo, we can say what's on average, the albedo of a pixel, given the amount of cold traps, surface and subsurface cold traps it has. When I say subsurface, I mean cold traps buried under a layer of this carbonaceous material that I talked about. Now, we can take the amount or the darkening of those pixels with latitude and compute the average brightening or darkening with latitude as we approach the pole, which is given by those green dots. So we can see that the average latitude is on the x-axis and reflectance is on the y-axis. So we see that the reflectance goes down as we go to higher latitudes. And then we can fit the model data to that information, or the model results to that data, and tweak the model parameters, basically the scale of cold traps, the lateral scale of cold traps, the size of cold traps, to get the or to make the model match the gathered data. And by doing that, we can use different lateral scales. So if, for example, if those small cold traps were on the scale of a kilometer, they would not be rough enough and bright enough to explain this decrease in brightness. And if they're maybe too small, or maybe too small, maybe because roughness increases with smaller scales. So maybe if they're too small, they're too rough, and they just get dark more quickly. But in between those two regions, the large and the small, there's the sweet spot, which is maybe between a meter and maybe a little bit smaller than a meter, which is the lateral scale of the cold traps that can explain the darkening that we see. Now that we have the lateral scale of cold traps, we can use the model that I've shown you before, the illumination model, to kind of try and estimate what would be the thickness of the ice. And one measure of the thickness of the ice is the measure of the depth of the shadow cast by the topography around it, right? Because the ice, at least an order of magnitude, or at least, sorry, a 0th order approximation, cannot really exceed the depth of the shadow, right? Because if ice, let's say you have a permanent shadow, the ice builds inside this shadow. At some point, it's going to be exposed to solar illumination. It's going to exceed the kind of peak above the permanent shadow and just sublimate. So the height of the permanent shadow is at least an upper limit to the amount of ice inside those small cold traps. And when you do this calculation, you find out that the thickness of the ice is between a meter, maybe 25 centimeters and a meter, something like that. So there's not a lot of ice basically trapped inside those micro cold traps, as you can imagine, which to me says one important thing, right? If you can imagine the case of the episodic deposition versus the case of continuous deposition of ice, considering those rates measured for gardening and photolysis, then continuous deposition, let's say there's enough, the continuous deposition is strong enough basically to, or is the rate of continuous deposition is high enough to resist the rate of destruction, then continuous deposition would always have a little bit of ice inside those cold traps. However, episodic deposition, like that, would slowly would accumulate, you know, at one point in time and then slowly disappear. Now, the fact that those micro cold traps are full, completely full, maybe hints that we're looking at something that looks more like episodic deposition, basically. Because we're looking at a point in time where we're like maybe like in between the place where the cold traps are fully full, let's say right after the impact of a large comet on the surface, and this state where there's almost no ice inside those cold traps. It just stands more to reason, right? It just stands to reason that episodic deposition can explain what we see now on the surface. Now, from radar deposits, so we can use, again, the large and the small cold traps to maybe say something about the mechanism. So the radar deposits tell us that the deposits, the ice deposits are pure, not mixed in with the regolith. So probably gardening is not the rate of gardening is probably not of the same rate of the accumulation. And the smallest cold traps tell us that probably a continuous deposition is impossible, because the chances that we'd see, again, when you take gardening into account, that we see such a thin layer on the of ice on the surface, and we can actually see that using spacecraft, probably tells us that the kind of the trickling rate of cold traps, if it exists, and because it's of the same order of the destruction rate, probably means that those cold traps should have been erased and not be apparent. Now, can we put more constraints on the amount of ice? And this is kind of a question I've asked myself a few years ago. And my guiding principle in answering it was very straightforward, nothing complicated about that. If there's ice inside craters, if there's a lot of ice inside craters, they should appear basically shallower, right? Because as we said, the hop length of water molecules on the surface is so big that it's almost like rain trickling into permanently shallow craters. There's no preference to one region over another region, basically. So you can imagine, someone once told me, you can imagine rain trickling into buckets, right? The buckets should be filled with almost the same amount of ice. Again, given no thermal effects, craters are not warmer than one another, etc. However, craters should be shallower, at least relatively. And this is very simple to test, right? All you need to do to test that is to look at the depth to diameter of craters near the pole of Mercury. So that's what we did. We looked at craters, relatively small craters, between 3 and 15 kilometers. They're not small per se. They're not 100-meter wide. They're not 100-meter wide craters, but they're a few kilometers wide. And the reason we kind of used 3 kilometers as the lower limit, even though this should be more pronounced in smaller craters, right? Because smaller craters, if they're filled with more ice, then the signal should be more apparent in those smaller craters. So the reason we used 3 kilometers, the lower limit in this range, is because we want to ensure that the resolution, the sampling resolution, was as high as possible inside those craters. And then after removing craters suspected in secondaries, we can see, and you can look at the key here on the top right, you can see that there are a lot of shallow, unusually shallow craters near the pole of Mercury relative to lower latitudes, where craters appear more purple. There's a high abundance of shallow craters near this region, and those are potentially secondaries of Prokofiev crater, which are easy to remove. We just basically remove the immediate region near Prokofiev. And when you take the average of depth to diameter with latitude across the pole of Mercury and plot it in this figure below, so on the x-axis you have latitude, and in the y-axis you have the depth to diameter of craters, you find that craters do indeed become shallower in high latitudes. And curiously enough, this shallowing starts exactly where models predict that craters should start accumulating ice based on latitude. And this is given here by the blue dots. So the green dots are craters. The gray dots are permanently shadowed craters, but craters that may be too warm to hold surface ice, and because of emissions and reflectance from the illuminated walls. And those blue craters, those blue dots, are craters that are both permanently shadowed and also significant, or also cold enough to hold ice for extended periods of time. And you can see that as those craters start to appear, so does the depth to diameter starts to decrease. Now, another interesting morphological property that we can look at is just the slopes, comparing the pole-facing slopes and the equator-facing slopes of craters. And when you do that, you find that the pole-facing slopes are slightly shallower than equator-facing slopes, which again contributes to this idea that the shallowing of craters and of slopes, this asymmetry kind of contributes to the idea that the shallowing is caused by the accumulation of ice. Now, Mercury is unique in the sense that it's found in a 3-2 orbital spin-orbit resonance with the sun. So as it goes around the sun, there are areas near its pole referred to as the cold and the warm poles, which are slightly warmer and slightly colder, respectively. And you can also calculate the distribution of depth to diameter in those cold and warm poles, those warmer and colder regions. And again, the craters inside on Mercury's cold pole, those colder regions, are slightly shallower than craters in its warm pole, which again indicates that the shallowing is potentially due to some thermal effect, basically volatiles. Now, when you repeat this exercise on the moon, when I repeated this exercise on the moon, I didn't expect to find anything interesting, because as you saw from the results I've shown you before, from the instrumentation data I've shown you before, the moon shouldn't have any thick ice deposits, or at least any pure thick ice deposits, because the radar reflectance of craters near the south pole of the moon is not as high as it is in Mercury, and certainly not related to the locations of any PSRs or all PSRs. Some craters are maybe unique in that sense, but it's not certain whether the radar reflectance inside some of those polar craters is due to roughness or due to the presence of ice. So we repeat the same exercise near the pole. We repeated the same exercise near the pole of the moon, and surprisingly found that the south pole, there's the same shallowing that we detected for Mercury appears also near the south pole of the moon, but not near the north pole. And this is an important clue. So it's important, A, because I think this precludes, or at least lessens our worries of some statistical error. So maybe, you know, maybe this region is just shallow because it's just unique in some sense. Or maybe there's some bias, some measurement bias that causes craters near the pole to be shallower. But since we don't see this behavior near the north pole of the moon, then we can, you know, not worry about any statistical or any bias in our measurement, or lessen the worries of any statistical or bias in our measurement. However, that's interesting, because if, like on Mercury, the presence of those shallower craters is caused by thick ice accumulated in them, why don't we see it in both poles? So that's kind of an interesting question that comes up when you look at this plot. And again, like we saw before, in high latitudes, the average depth to diameter decreases near the South Pole, but not near the North Pole, where it's constant, almost constant. Now, I should just say that if you measure the shallowing, both on the moon and Mercury, you get that it translates into a shallowing of a few tens of meters, at most, I think 50 meters for the moon, maybe a little bit more for Mercury, which, again, at least potentially indicates, or at least when you naively observe this, look at this data, indicates that there are thick, between 10 and 50 meter thick ice deposits on the moon that were invisible to previous remote sensing instruments. Now, could this be just a fluke, just a statistical fluke? Luckily, this amazing catalog by Stuart Robbins that came out in 2018 helped us answer this question. We measured the depth to diameter using the same method of all those lunar craters all across the surface, and again computed the mean depth to diameter with latitude. And we again see this shallowing, significant shallowing, only near the South Pole and not anywhere else. There's more noise near the North Pole, as you expect, because there's less data, but definitely not shallowing. I mean, the average of that is the same as it is in lower latitudes. The shallowing that we saw before, the depth to diameter decreases only near the South Pole. Now, there are many other explanations that can explain, this shallowing that's not related to ice. So let's quickly go over them. I don't have a lot of time, but just let's quickly go over them. I'll just say that if you're interested in the paper, we kind of outline the reasons why we believe this is ice, not some other process. So one option is secondary craters. Secondary craters are formed by fragments of the surface. And once a primary crater forms, it ejects ejecta and those large rocks that form secondary other craters close to the point of primary impact. And those secondary craters usually are, because of the lower impact energies, usually are shallower than primary craters, the craters that form because of meteoritic impacts. So to test that, all you need to do is look, is ask yourself whether the shallowing you see is due to a kind of a local phenomena, because secondaries tend to be a local phenomena. And you can again bin the results by, for example, quadrant. So you can look at longitudes, between 180 and 270, etc., and see that, for example, on Mercury, the shallowing is almost the same in all quadrants. So it's not a localized effect. Actually, in the secondary heavy quadrant near Prokofiev crater, craters are always shallow. So it's not, so secondaries don't really cause shallowing. They just cause a shallow quadrant, a shallow behavior all across the surface. On the moon, again, the same shallowing is observed. On the moon South Pole, the same shallowing is observed across all 4 quadrants. And near the north, there's no shallowing in any quadrant. So it's not a localized effect like secondaries. Could it be just a large-scale geologic deposit that kind of blankets the pole? Well, one way to do that is to look at those craters that we looked at, the 3 to 15 kilometer craters that we looked at, inside and outside larger basins, larger craters, because those larger basins potentially removed this blanket as they were formed, as they formed near the pole of the moon. And if they remove this, unique geologic deposit that makes craters appear shallower just near the pole, then the effect would not happen inside them. However, we do see the same shallowing inside and outside those larger craters. And we can also, of course, compare our results geologic maps. But again, there's no spatial correlation with any major geologic deposit that may cause craters to become shallower. Could this just be like an older eroded region? Maybe the moon is very young, and older eroded regions, because craters in them are older, they just, due to relaxation and other properties like gardening and mass wasting, they just become shallower. The rims become less crisp, and the craters themselves become less deep, more shallow. However, there's no correlation between the depth to diameter and the amount of craters in each aerial bin, which may indicate a correlation with age. So this is not a behavior that's dependent basically on age. It's not like those older bins are much shallower than other bins. And here's a story that we came up with that I think may help explaining what we see on the moon. So basically, in the past, a potentially a large comet impact, because we said the most probable explanation is potentially an episodic deposition. So a large comet impacted the surface of the moon, or a series of large comets, maybe when the solar system was more populated with large icy objects that kind of just went around hitting planets. So it could be that with time, so the ice was deposited in this time and was slowly covered by regolith and kind of got mixed in, or the regolith kind of got mixed in. I hope you can hear me. Got mixed in with the ice, causing the regolith the ice to be less pure. And this is the reason we don't see it in radar, basically. So it's not that it's very thin, it's just that it's mixed in with the regolith. And again, we can compare the pole-facing versus equator-facing slopes on the moon, and we again find that they're slightly shallower, the pole-facing slopes, relative to the equator-facing slopes. Another interesting exercise another interesting exercise would be to try and correlate the presence of surface ice that was indicated by the paper I showed you before, the Lee paper from 2018. And we do see that craters with more surface ice in them tend to have a shallower, or tend to be shallower, tend to have a lower depth to diameter, which may be telling of some connection between the subsurface ice that's buried inside those craters and that's invisible to radar, and those surface deposits that we see by those instruments. And I'm not really going to talk about that. I'll just say that the next step, basically, is to try and see what happens to those ice deposits, those once pure ice deposits, once they're exposed to gardening. Whether this explanation of ice deposits that were covered by regolith and gardened with time and mixed in, again, got mixed in with the regolith with time, is plausible or not. And to do that, we use a model that I recently developed that looks at layers of ice and regolith in the subsurface. So it's kind of a combination between a Monte Carlo simulation of crater formation and of cratered surfaces formation, and kind of a mixing gardening algorithm or a model, basically. So what you see here, for example, the green layer is ice and the red is regolith. And as this crater forms, it ejects ice in the subsurface, kind of on the surface. And using this 3D kind of mixing models that I'm showing here, we'll try to further investigate whether this explanation of ice that was once pure and got gardened with time is plausible or not. And again, I'm not really going to talk about that. I'll just say that, because I'm really out of time, I'll just say that, just conclude that we know there are ice deposits trapped in cold traps near the poles of both Mercury and the moon. And we see in instrumentation that the amount of ice is trapped near the poles of Mercury is significantly greater compared to that trapped near the poles of the moon. And we can constrain, using observations and models, the mechanism to be episodic and probably not continuous. And this is also supported by other results. For example, the crisp edges of the images of the ice in images that I've shown you before, or in just the beginning of this presentation. And then finally, we find this morphologic evidence in craters that the quantity, the amount of ice on both planetary bodies may be comparable, potentially, which may resolve the question of the difference between them. Because I think the easiest explanation to why there could be a difference in the purity, in the amount of ice between those two bodies, is just that maybe there's no such difference. And all the difference that we actually see, or the difference, for example, in radar and reflectance, the coherence and the thickness of the ice on those two planetary bodies, is just the result of more erosion that happened and more mixing of regolith that happened on the moon, but not on Mercury. And future work is try and understand the role of the thermal leg that I told you about, this thick carbonaceous layer, which acts as a thermal leg, and compare this to the absence of the similar thermal leg on the moon, and see if the absence and the presence of this thermal leg and its mixing can really explain the higher purity of ice deposits on Mercury relative to ice deposits on the moon. And at that point, I want to thank you. And if you have any questions, I'll be happy to answer them.
Yeah, thank you very much, Leo. Very, very interesting talk, because we learned about this. I had to look up your paper to see the definition and meaning of the micro cold traps, you know. That's something.
Yeah, so those are not really micro, they're referred to as micro cold traps. This is a concept that was formulated by a scientist called Paul Hain, actually. And they just published an interesting paper. I really invite you to read it last year on cold traps on the moon. So the cold traps we're looking at are not really micro in that sense. They're just referred to as micro cold traps. They're actually small scale cold traps. That's a more appropriate name for them. They're on the order of meters, maybe tens of centimeters.
Okay, thank you. So there's one question from Yahui Huang, and can you read it? Can you read that question on the chat box?
Yeah. How much those typical depths of shadow are affected by local or regional topography from nearby large craters in your model? Which model is that? I'm sorry, I'm not sure which part of it.
Hello.
Hi, hello.
Hey, can you hear me?
Yes, I can hear you.
Okay, yeah. So like, I think that is in the section when you were talking about like, the topography can create the PSR.
You probably refer to, let me find that slide. The slide?
Yeah, this one.
Uh-huh.
So yeah, so the Gaussian random models, like, so I just want to have you consider.
That's a really good question. Yeah, that's a really, because you're right that to really get the full picture here, we have to consider both larger topographic effect, like regional topographic effects, like you said, and also local. However, when we look at the smallest surfaces, as long as we're not looking, for example, exactly at the wall of a crater whose slope is 45 degrees, 40 degrees maybe, then it's okay to kind of neglect those regional slopes. But you're completely right that to get the full picture, you have to take into account both the regional slopes and the small scale slopes. In this case, because we're interested in kind of an average statistical picture of how the pole looks like, then we ignore those larger regional slopes and only looked at those micro small scale slopes, which we use to infer the mechanism and time of deposition of ice.
Okay. Yeah. So yeah. I think thanks. That makes sense. And also like, in this model, it's I guess that is similar to the north or south pole of the moon. So that also consider the moon's obliquity, the direction.
Yeah, so you can simulate the obliquity. Basically, you simulate the angle of solar radiation relative to the surface. So you can compute, you can take the obliquity into account when you're doing that. Yeah.
Okay, that's cool. Thank you.
Sure. Thank you.
Okay, one last question that I have from me is just to say what is the difference? Why is the north-south symmetry of the lunar polar ice deposit?
That's the $1 million question, I think. So maybe I'm going to show you an image that I think. So the reason I'm stuttering because the answer is that I don't know the difference. However, there's a large difference between the geologic maps of the north and the south pole of the moon, as you can see here. So near the north pole, you have this almost triangle. I don't know if you can see it here. That's the result of potentially depositions of deposition from basins or from a basin that's located in lower latitudes, who's potentially deposited material all the way up to the pole. And one idea that we had is that the material deposited by this basin was so hot that it caused significant differences or that it changed the thermal environment of the North Pole relative to the South Pole significantly, causing maybe the destruction of coal traps near the north, but not near the south. So this is one idea. I'll just say that we are not really sure about what's going on in the north. Maybe I'll go back to another map that kind of explains what I'm saying. So in the south, as you can see here, most of the detections of ice made by Lee and others are within those PSRs. So you have a lot of ice. It's always inside PSRs, and it's a pretty clean picture. In the north, the topography looks much different than it does in the south, right? There are no large coal traps. And even inside those coal traps, the amount of ice is significantly lower than that of the north. So there's some inherent difference between the North Pole here on the left and the South Pole here on the right that I think is not yet well understood and constrained. So instead of an answer, I only raise more questions. It's like the way of the scientist. But I think the difference between the North and the South can maybe the topographic difference, in addition to the geologic difference, can maybe help us get a sense of why they're so different in the amount of ice they harbor.
Okay, thank you. There's Professor Nakagawa has a question to you. Can you read it?
Yes, I'm curious how important is bombardment of solar wind particles for destroying ice? That's another really excellent question. And this balance between solar wind destroying and actually causing accumulation of ice has been well studied in the past 2 decades. So it's interesting because solar wind can indeed destroy ice, like you said, but it can also cause the accumulation of ice. And the reason is those free H- ions basically can attach to minerals on the surface of the moon and turn into something that looks like water, basically. So solar wind can both destroy and help or encourage the accumulation of water near the poles of the moon. And the short answer for your question is that from many considerations, on the moon, there's more accumulation than destruction, and on Mercury, it's the other way around. But the role of those, while it is important, is probably less important than the role of, for example, galactic rays, right? Like high radiation, highly energetic particles coming from the galactic center, for example, from the rest of the universe. Because I want to remind you that because the moon has no magnetic field, the craters found near the pole can't really see the sun, so they can't really feel the impact of those solar wind particles that can potentially destroy the ice. So I'd say it's important to some sense, maybe not as important as other factors in destroying ice.
Okay, very good. We'll look forward to your other talk, very soon about this.
In the future.
Yeah, you're working, you're very hard and very interested in work. So we will conclude this talk now. We thank Dr. Rubenenko, for a very exciting, inspiring talk, and his last picture about his Monte Carlo model is also very interesting. I'm going to chase after him about that. But then we have to end this session now. And please, for the audience, that we still have 2 talks in the afternoon. One by Professor Patty Lin, National Taiwan Normal University. She will talk about the moonquakes. And the other one will be given by Dr. Simon Locke of Caltech. He will talk about the synergia. So those are very interesting things. So you're very welcome. Thank you.